Bismillahirrahmanirrahim. Assalamu alaikum. Welcome back to Physics Mathematics Hub. In today's video, we'll explore a fascinating topic, the Balmer and Paschen series of hydrogen. So stay tuned. Exercise 1.28. What are the longest and shortest wavelengths in the Balmer and Paschen series for hydrogen? Given data: Balmer series, when electrons jump from higher level to the n equal to 2 level. Paschen series, when electrons jump from higher level to the n equal to 3 level. Required data: first we have to find the longest wavelength in Balmer series, which is denoted by lambda, B for Balmer and max for longest. Similarly, shortest wavelength in Balmer series is represented by lambda B minimum, and longest wavelength in Paschen series lambda P maximum, and shortest wavelength in Paschen series lambda P minimum. Before diving into the mathematical calculation, let's briefly review what the Balmer and Paschen series are. The spectral lines of hydrogen arise when electrons transition between energy levels in the atom. When an electron falls from a higher energy level to a lower one, it emits a photon, and the wavelength of that photon corresponds to the difference in energy between the two levels. Well, the Balmer series occurs when electrons fall to the second level. The emitted light is in the visible region of the spectrum. Similarly, Paschen series occurs when electrons fall to the third level. The emitted light is in the infrared region of the spectrum. As we have got the basics down, let's calculate the longest and shortest wavelengths in both series by using Rydberg formula, which is 1 over lambda is equal to R into 1 over n1 square minus 1 over n2 square. This is equation 1, where lambda is the wavelength of emitted photons, R is Rydberg constant, which is equal to 1.097 multiplied by 10 to the power 7 per meter, and 1 is the lower energy level, which is 2 for Balmer series and 3 for Paschen series, and 2 is the higher energy level, starting from 3 for Balmer and 4 for Paschen series going upwards. Now let us calculate the longest wavelength in the Balmer series, where the electrons fall from the nearest higher level, which is third energy level. Here we use equation 1, 1 over lambda B maximum is equal to Rydberg constant 1 over n1 square minus 1 over n2 square. Putting values, we have 1 over lambda B maximum is equal to Rydberg constant into 1 over 2 square minus 1 over 3 square. Simplifying the terms in the bracket, we get Rydberg constant into 1 over 4 minus 1 over 9. Taking LCM, we get 1.097 multiplied by 10 to the power 7 per meter into 5 over 36. Further simplification gives 36 over 5 into 1.097 multiplied by 10 to the power 7 per meter. Multiplying pi with the 1.097, we get 5.485, and transferring 10 to the power 7 per meter from the denominator to numerator, we get 10 to the power minus 7 meters. Simplification gives lambda b maximum is equal to 6.56 multiplied by 10 to the power minus 7 meters. In terms of nanometers, we get 656 multiplied by 10 to the power minus 9 meter, which is the required longest wavelength in Balmer series. This wavelength shows red light which is visible to human eye. Similarly, the shortest wavelength in the Balmer series where the electrons fall from infinity, the highest level. We again use the same formula, 1 over lambda b minimum is equal to Rydberg constant over n1 square minus 1 over n2 square. Putting the values we have here, we put n2 is equal to infinity, which gives us 0. 1 over infinity square is equal to 0. Simplifying, we get lambda b minimum is equal to 4 divided by 1.097 multiplied by 10 to the power 7 per meter. Similarly, finally, we get 364 nanometer answer, which is the shortest wavelength in Balmer series. This wavelength lies in near ultraviolet region just below the visible light spectrum. Now we are going towards the Paschen series. To find the longest wavelength in the Paschen series, where the electrons fall from the nearest higher level, which is the 4th level, using equation 1, here 1 over lambda p maximum is equal to r 1 over n1 square minus 1 over n2 square. Putting values, we get 1 over 3 square minus 1 over 4 square into Rydberg constant. Simplifying, Rydberg constant into 1 over 9 minus 1 over 16. Further simplification and taking LCM gives 1.097 multiplied by 10 to the power 7 per meter into 7 over 54. Further simplification gives lambda p maximum is equal to 144 divided by 7 multiplied by 1.097 multiplied by 10 to the power 7 per meter. Finally, we get 1875 multiplied by 10 to the power minus 9 meters, which is equal to lambda p maximum is equal to 1875 nanometers, which is the longest wavelength in Paschen series, and this wavelength falls in the infrared region of the hydrogen spectrum. The shortest wavelength in the Paschen series occurs when the electrons fall from infinity to the third level. Again using the same formula, putting the values. Here we put n2 is equal to infinity and 1 over infinity square is equal to 0. Simplifying further, we get 1 over lambda p minimum is equal to Rydberg constant into 1 over 9. Simplifying further, we get lambda p minimum is equal to 820 multiplied by 10 to the power minus 9 meters, which is equal to 820 nanometers. This is the shortest wavelength in the Paschen series, which falls in the infrared region of the hydrogen spectrum. I hope this video helped you understand the concept of spectral series and their wavelength. If you enjoyed it, don't forget to like, share and subscribe to Physics Mathematics Hub for more physics and mathematics content. Thanks for watching and see you next time. Allah Hafiz.